Today we're going to be looking at the definition of continuity. The idea of continuity is that when we're given a function f of x and a real number c, we want to compare the values of the limit as x approaches c of f of x with the value of f of c itself. We've seen that when we calculate the limit as x approaches c of f of x, we don't pay attention to what happens exactly at x equals c, but to calculate f of c, we just plug in x equals c into the function. And so the idea of continuity is when we're going to compare these two values, and we want to know what happens when these values are different or what happens when these values are the same. Let's walk through a couple of examples to motivate our definition of continuity. So first, consider the function f of x equal to x squared minus 4x plus 3 all over x minus 3. And again, we want to compare the two values of the limit as x approaches 3 of f of x with the function value f of 3. First, we'll find the limit as x approaches 3 of f of x. To do this, we're going to factor the numerator and then use the cancellation theorem. So the numerator factors into the quantity x minus 3, x minus 1 over x minus 3, and then my x minus 3's cancel. So I'm left with the limit as x approaches 3 of x minus 1, and now I just have a polynomial. So to evaluate this limit, we just plug in x equals 3. So we get 3 minus 1, which equals 2. So the limit as x approaches 3 of f of x is equal to 2. Now let's compare that to the value of f of 3. If I plug in x equals 3 into the function above, we see that we would end up with a 0 in the denominator. So f of 3 is actually undefined. So we see that these two values, the limit as x approached 3 of f of x was equal to 2, while f of 3 was undefined. So these two values were not equal to each other. Let's look at the graph of this to see what happens. We can see that as x approaches 3, the y values approach 2, so we do have that the limit as x approaches 3 of f of x equals 2, but at that specific point, x equals 3, we have a hole because our function was undefined at that point. So in some sense, our graph is disconnected at this point. This is one example of a way a graph can be discontinuous at a point, is to have something like a hole where it makes our graph disconnected in some way. Next, let's consider the piecewise function g of x equal to x squared minus 1 when x is less than 2, and the square root of 3x plus 3 when x is greater than or equal to 2. And again, we're going to be comparing the limit as x approaches 2 of g of x with the value g of 2 itself. Since g is a piecewise function, to talk about the two-sided limit, we'll have to first compute the one-sided limits. So first, let's do the limit as x approaches 2 from the right of g of x, which will be the limit as x approaches 2 from the right of the square root of 3x plus 3, because everywhere to the right of 2, g of x is the same thing as the square root of 3x plus 3. Using the power rule, I can rewrite this as the square root of the limit as x approaches 2 from the right of 3x plus 3. And now I'm just taking the limit of a polynomial, so to evaluate that, I just plug in x equals 2. So we have the square root of 3 times 2 plus 3, which equals the square root of 9, which equals 3. Now let's compute the limit as x approaches 2 from the left of g of x, which will be equal to the limit as x approaches 2 from the left of x squared minus 1. And then again, because I have a polynomial, to evaluate this limit, we just plug in x equals 2. So we get 2 squared minus 1, which equals 3. Now, because the left-hand limit and the right-hand limit were both equal to each other, I can say that the two-handed limit as x approaches 2 of g of x is also equal to 3. Now let's compare that with the value of g of 2. Since this is a piecewise function, we need to see where we plug this in. So because we're looking at x equals 2, that will get plugged into the bottom part of this function. So g of 2 equals the square root of 3 times 2 plus 3, which equals the square root of 9, which equals 3. So in this example, we have that the limit as x approaches 2 of g of x and the value of g of 2 were equal to each other. Again, let's look at the graph to see what happens. Here we can see that as x approaches 2, my y values approach 3, and then also if I plugged in the value x equals 2, we would get the y value of 3. So the limit and the function value meet up at this point right here. So this graph is connected in a way. If you tried to trace this graph, you could do so without picking up your pencil. So some of you might have heard that idea of continuity before, that if you can draw a graph without picking up your pencil, then the graph is continuous. But the technical definition deals with combining the idea of the limit and the function value being equal at that point, so that your graph is connected rather than disconnected, as we saw in the first example. So here's the technical definition of a function being continuous at a point. A function f is continuous at a point x equals c if the limit as x approaches c of f of x equals f of c at that point. So this definition contains three kind of parts to it. So for a function to be continuous, we need f of c to be defined, unlike the first example that had a hole. We need the limit as x approaches c of f of x to exist, and then those two values have to be equal to each other. That the limit as x approaches c of f of x has to equal f of c. If any one of these three parts of the definition is not satisfied, then we say the function is discontinuous at that point.